Hello, everybody. Welcome to this physics lecture, and in this lecture, we are going to be talking about the idea of momentum. Now, why do we discuss momentum? We have all of these other ways of talking about motion. We have kinematics, dynamics, we have energy. So, why do we care about momentum? Well, momentum does two things. First is it describes motion much like we describe motion with our energy. We'll see that, like energy, momentum is a conserved quantity, so it's useful in that sense. But what energy lacks, when you think about kinetic energy, what energy lacks is this idea of direction. When we talk about kinetic energy, we don't include is it moving to the left, right, up, or down. We just say kinetic energy is related to a moving object. Whereas if you think back to dynamics, dynamics is very specifically talking about a direction it's moving in. So momentum, unlike energy, includes this idea of direction. So that's really why we care about it. But that begs the question, what is momentum? What do we mean when we say momentum? And very basically, when we talk about momentum, very basically, we are talking about an object's, the difficulty, you might say, how hard is it to stop an object. An object that is harder to stop, we would say, has more momentum. So that's the idea. We are going to talk about that today. So jumping into this lecture, we have two goals, really. Our two goals are going to be, first, can we explain what momentum is in physics terms, not just say how hard it is to stop, but more physically, can we describe what it is? And then the important part, how to calculate momentum. We want to know how to calculate it. So when we talk about momentum, we first ask, what is it? It's how hard it is to stop an object, but how do we describe that physically? We think about the objects in our everyday life, and we think about perhaps a toy car. Here's my drawing of a toy car. Our toy car might move at perhaps 3 meters per second, how fast it's moving. And then you could imagine a real car, not a toy car, but an actual vehicle, moving same speed, 3 meters per second. And you ask the question, well, which is harder to stop? And it's pretty obvious. The real car is probably more difficult to stop. Well, what is the difference between these two objects? They're both cars, certainly. But what is the real difference between them? The real difference is mass. The real car has a larger mass than the toy car. So we would say that mass probably has something to do with this momentum idea, because something with more mass is harder to stop. Okay, well, what else might we think? We think of a baseball, perhaps. Here's my drawing of a baseball. My baseball is moving perhaps at a relatively low 3 miles per hour. It's just sort of lobbed in some direction. But you think about that baseball being thrown by a professional pitcher. Professional pitcher can probably throw close to 100 miles per hour, much quicker. So you ask the question, well, which is harder to stop? And I think the answer is pretty obvious here again. The baseball that is moving at 100 miles per hour is much more difficult to stop. So we would say baseball is moving 100 miles per hour. More difficult to stop. That is the one that has more momentum. Well, what is the difference? They both have the same mass. It's the same baseball in both cases. But the difference here is the velocity. The velocity is different in each case, and the one with a higher velocity is harder to stop. So this leads us to the idea that what is momentum? Momentum is the difficulty it is to get an object to stop, which seems to depend on the mass as well as the velocity. So we say this quantity of momentum must be equal to, well, probably that mass multiplied by the velocity of the object. And this gives us our momentum. Now we like to create a physical unit here, or not physical unit, a representation for a physical quantity here, like we do with everything, right? V for velocity, M for mass. What do we use for momentum? Well, for momentum, we actually use the letter P. So we say momentum, P, is equal to mass times velocity. And velocity, well, that is a vector, so I'll put a vector arrow on it. Mass is a scalar quantity. It doesn't have direction, meaning the only other vector here is momentum. Momentum is mass times velocity. Momentum is a vector, meaning it has directionality, and we'll jump into that more a little bit later on. But for right now, we'll just say momentum is mass times velocity. Good enough for me. And more specifically, if we were looking for the magnitude of the momentum, which we will be doing for the rest of this video, the magnitude of mass is given, the magnitude of momentum is given by mass times the magnitude of velocity, or in other words, the speed. And that's what we'll keep for right now. So we look at a couple of different objects. Perhaps. Let's think about, maybe we have a container. My poorly drawn container. And our container has a bunch of molecules in it, and these molecules, as molecules do, zip around. They zip around at quite high speeds, so we'll put an arrow here representing that they are, in fact, moving. We have a container of molecules moving. You might also imagine a soccer player kicking a soccer ball. And after the soccer player kicks the soccer ball, it is now moving. Okay, well, that is another moving object, and with all moving objects, we can describe momentum. And finally, I am going to draw here a picture of a ship. So here's my picture of a ship. We look at these three objects. The question is, what might we expect their momentum to be? And for each of these, we might think, how hard is it to stop each object? Well, the boat here is very large, moves at a relatively fast pace, so that probably has the largest momentum. So I'll say P large. If you think about a soccer ball, you get hit by a soccer ball, kind of hurts a little bit, but if you get hit by a molecule, it probably won't even affect you. You're hit by molecules all day, every day. So you might look at this molecule and say this is probably where the smallest momentum is, and then the soccer player has the medium amount of momentum, has the middle amount of momentum. And we can actually calculate this, right? We can calculate the momentum of different objects. And as an example, let's go ahead and calculate the momentum of, we're going to do two objects here. So I'll split the screen in half. We'll start with the momentum of a molecule. Molecules typically will have a mass that is very, very, very tiny. In fact, for some molecules, we can estimate the mass to be about 6 times 10 to the minus 25 kg. This is going to be an object that is a molecule of air, This is a molecule of air that is roughly room temperature, will have about this speed. This mass, and it will have a speed of about 500 meters per second. Molecules move quite quickly. So you ask, well, what is the magnitude of the momentum? And no, I do say magnitude very specifically. What is the magnitude of the momentum? Well, you take the mass of the object, you multiply it by the velocity, take those two, multiply it together, and you'll end up with a momentum of 3 times 10 to the minus 22. And then we ask about the units. The units are going to be mass, kilogram, times velocity, meters per second. So you get this very, very, very tiny momentum, meaning it's very easy to stop a molecule. And again, you're interacting with molecules all the time. They're hitting you over and over and over. So that's the the momentum of a molecule. Well, what about something a little bit larger? Let's ask about the momentum of a car. Cars are quite large. Cars can typically have masses somewhere in the thousands of kilograms. Let's assume 1,400 kg. How fast does a car move? Well, a car can move pretty quickly, and we'll say 15 meters per second for this example. So you have a car moving at 15 meters per second. You're asked, what is the momentum? The momentum, again, can be found by mass times velocity. Here, where we're looking for the magnitude of the momentum, we just take the mass and multiply it by this 15 meters per second speed. We are ignoring direction for the moment. You multiply these together and you'll find 21,000 kilogram meter per second. So that, again, is our unit of momentum, kilogram meter per second. You might ask, do we have some special unit to take that place, right? We had force, we named a new unit of Newton. We have energy, which we gave a new unit of joule. Do we have anything like that for momentum? And the answer is no, actually. For momentum, we do keep it in this kilogram meter per second. So then we have this idea of momentum. We ask the question, can we explain what momentum is? Well, momentum is simply how difficult it is to get something to stop, which can be found with a calculation of taking the mass of an object and multiplying it by its velocity. All right, so that's it for this video. I hope that it was clear. If you have any questions, please feel free to ask.